So what was it? Yeah, it's a ship. Yeah. So there was a ship that was coming into port, and it needed to have some equipment thrown out to it. So something like this tower. So we had a projectile. This was D. This was D. Now D was actually the original distance where it was a shot. It was the position that the plane, the boat was when the thing was shot. Then you shoot the projectile at a particular angle. It was, what remind me, was it 60 degrees relative to the vertical, or relative to the horizontal. So we can look data. And it hit the boat. And so it was initial velocity. And I think this distance, the height of the everything was 8.5 meters. Number. So that was the same distance. So this distance here was it 8.5 or 8.85?
8.75.
8.75. Okay. Subscript D here, yeah. So that's you know, you have to maybe come up with your own names for the subscripts, but that's one way I would do it. So 8.75. This speed of the ship, what was it? It was something centimeters per second, I think. What was it? So I called it VS, I think. And this was the projectile, so VP naught. What was the speed of the ship?
$4.25. Oh, sorry.
I need some units. What?
45 centimeters per second.
So, centimeters for what? It can't be just centimeters.
Per second.
Seconds, right? Thank you. Yeah. Centimeters per second. And this speed was, what was the initial speed of the projectile? Anyone? What was the initial speed of the projectile? It was at 60 degrees. Yes. Yeah. Okay, so what I had shown you was this a quick and dirty version. So this thing is parabolic motion. It has all its equations, the 7 equations. This thing is constant motion. So we really, I kind of reduced that to, I guess, 2 equations or 3 equations. Really. First, So this guy, you know, I called it. So basically, it starts at some position D, and they both meet at some other position. That position is here. So like if I superimpose my x-axis, maybe that's a better way to do it. I think a lot of people, some people seem to have difficulty visualizing that the other day. Let me put in an axis. So this is my origin. I'm going to place right at the vertical distance below which the projectile is shot. All right. So the initial distance D is someplace back here where you shoot the projectile. So I'll call that D. But that's what we're looking for. But the ship is moving as projectile comes. And so they meet at some other position, which I'm going to call, it's the final. So you start your clock whenever you shoot projectile, then the initial position of VP of the projectile is the origin 0, and the initial position of the train is D. So in fact, let's write that over here. So again, here, this is where the subscript is coming from. X S naught is equal to D, and X P naught is equal to 0. So then they come forward and they hit at some point. Let's call that X. Well, I just can call it X, but it's the final position, XS of the ship. That equals the final position of the projectile. They're the same. So I'm just going to call that XX. Right? So, but all that's implicit information. That's how we, you know, those equations that are going to come in to be valid. In fact, let's call this equation 1, this equation 2, and this is equation 3, XS equals XP equals X. Yeah. So now the equations of motion. One for this guy, and that's just going to be, I'll call that equation 4. And that's its final position, X, equals its initial position, D, plus velocity, its constant speed, time to time at which it is traveling. Now, actually, that's another equation, isn't it? Let's make this equation 5. Let's say something about the time. Technically, the time that this happens, if I start my clock at T naught, it's T, the initial time for both is the same. But when they get to this position, the same amount of time is transpired. And that time is, you know, technically you can call that a TS, but that's the same time as TP. The time it takes this to travel along this displacement is the same time it takes this guy to travel along this parabolic path. But that's all the same time. Again, the final position and the final time are the same. They hit, they're simultaneously at that position at the same time. So the time that's transpired, I'm just going to call that T. So that's actually the fourth equation. Right there. TS equals TP equals T. There's just one time. So I'm going to call that equation 4. This is 5. So as opposed to calling that TS because that's about the ship, I just can call it T. Then I have the equations associated with parabolic motion. And with that, I guess I could just go to, yeah, so we just write the first couple. We have the velocity equation V. V P final equals V naught plus the separation. Well, I guess I actually have 2 equations for that, don't I? I could break it up into parabolic motion. Let's do that. I've got the equation along the x direction, the constant equation, and the equation on the y. So let's just say I can maybe do, so this is for the ship. And now this is for the projectile. So we'll just use the first two equations of motion. The one in for the x direction. And that is, the x direction is the final x position, which is x, equals the initial x position, which was 0. So x p naught was 0, plus v v naught x vp vp naught x times t. And then the y equation. So there we were at the first couple. The y equation we have one is vp vpy equals vpy naught, which is 0 actually, minus gt. And then the y equation, which is the one that I was really using, is y equals y naught plus vy naught p vy p naught v p naught y times t minus g t squared. So there are 4 more equations for this, but for the projectile, but we only need, we only need these few. So what I had done is shown you that these two positions are, these two equations, this x is the same. So we can equate those two things. Right. And if we equate them, then that leaves one unknown, which is time. And we take that, solve that equation with time and stick it into here. And that gives us a quadratic that we can solve and get the time and then work back. So basically I was using that equation, and that equation. Now, yeah, so what some people had done, what one person had suggested, was to find the time, which you still have to do by, you could probably use some other equations to do that. If you find the time, you can put the time back in here to get x, then put x in here, and the time that you have, basically, and solve for d. It's basically the same thing I'm doing, but kind of a different mathematical perspective. So go ahead and work on that now. See if you can rewrite, get back to that, and then solve for that helps a little bit. So you equate these two, right? X, solve for t, take that and put it in here, t, and then solve that quadratic t, and work backwards to get the distance t. Right. Oh, actually, no. I mean, that's the same. But when you saw that quadratic, it's going to be a quadratic in terms of t that you can solve for quadratic. Well, actually, yeah. You could just directly do that. So, yeah, a couple ways. I'm gonna let you just try to go for it. Let me just get this up. But yeah, it's basically a couple ways you could probably approach that. But that's everything is there. So give it another shot. And while you're doing that, I'm gonna start all right. Is someone saying something? Just so you're cutting out, I can't hear you. Sure. Sounds like it's probably about round. You should see it there now. So you can, if you've already finished, you want to start uploading at a time that you can. I'm back now. I can see you. Is someone trying to say something? Is that just some background noise? One question. All right. This 4-1 step forward. So unknowns, basically at this point I have 3 unknowns left. And the 3 equations that I use are these equations, the ones I pointed out to you. So 3 unknowns are x, t, and d. So again, I want you to try to work through this thing, but if I equate these two, equating x 5 and 6, and what I have is d plus vp naught x times t equals this guy, basically VP, no, sorry. X equals D times V times T. And that V is VS actually. It's constant, so it's not initial or final, so it's just constant. So then this is VS and times T, and that equals this thing, VP naught X times T. So it's a little different than we had yesterday, I don't know. But D then is equal to, and I take it over and take out the T, I have T times VP naught X minus VS. Yeah. So the unknown that I need to find is time, because these two things are known. And once I find that, I see, and I got it. So what that showed me is I can go here to get the time. And in this case, I guess I don't really need to stick it. I could, I mean, you could do, I initially said do something like solve this for T and stick it in there, and it will, but it'll just convert it to a quadratic in D. What you could just do is just solve this for T, and then stick the T in here. So that's why I'm encouraged. I want to do it that way now. So XP naught is, XP final is 0. So from 8, that falls to the ground. It's the final position of that. So we have 0 equals Y P naught plus. Now I'm going to stick into this. The VP naught, Y, that's VP naught sine theta. Remember, VP naught, not sine, is it sine? It's sine, yeah, sine theta naught. Sine of 60. That's what this thing is, times T minus 1/2 G T squared. And again, remember, if I'm shooting this at a projectile, you have an angle of 60 degrees with respect to the horizontal. It's V naught or VP naught. Then I have and actually this thing here is VP naught cosine theta, VP naught X. So I should probably go back and put that in. So VP naught X equals VP naught cosine of theta. And that guy is VP naught sine of theta. That's just theta naught. So just to be, just let me go ahead and put that back in. Should I do it? No, I'll leave it there. We'll do it later. Well, I guess I should do it now because I just want to rewrite the numbers. So,
Professor, your mic's lagging. And your camera also, it's
okay,
blurry.
I don't think I can do anything about that.
Your camera is blurry also.
Yeah, I don't think I'll be able to do anything. Can you hear me? I guess I'm lagging. Yeah, I think it's a signal. I can't do anything about that. But if you can just follow along in the meantime, it's still going to be able to see it. Can you see it at all?
No, it's like blurry.
Okay, well, you can hear me pretty well, even though it's lagging. I think maybe activity picks up in the afternoon, and maybe that's why it gets like the signal gets bad. There's more people on the network. That might be one explanation. Because you know, I didn't do anything. I was been teaching since 8 o'clock this morning. We didn't have a problem earlier. Yeah, perhaps possible. I don't know if it's by my bandwidth, because if it were low, it would be low all the time. And unless it goes in and out, I don't see why. I think it could be more people on the network or something. What do you mean the bandwidth is low? Like would it fluctuate? The bandwidth fluctuate throughout the day? That doesn't, it seems like the signal would fluctuate, not the bandwidth. The bandwidth is what it is. It's not low. I mean, I don't have this problem all the time. So what do you think? Casey? Really? Maybe that just means the signal is weak or something. So it could be that. I don't know. Yeah, it seems like it only happens in the afternoon. It's only happened with this fact. I think is that any better? Yes, no?
No.
Yeah, I think it's, I don't know how to solve the problem. Hopefully we get that in. I'm sure I don't have any control over that. Um, let's give some time maybe to clear up. I'm gonna keep moving on here. Saying it's better, D here?
Yeah, it's good now.
Okay. Yeah, all right. So I'm going to go ahead and stick the cosine theta in there for equation 10, I guess. I'm going to just do it right here, so I'm writing it in. So given that's the case, this becomes VP naught cosine of theta naught minus VS times T. So we solve equation, remember the quadratic equation. Remember that is A, so 0 equals C plus BX plus AX squared, and X equals minus B plus or minus the square root of, B squared minus 4AC over 2A. So quadratic equation, quadratic formula. So that's what we're using to solve this. So in our case, B is equal to YP naught. C is equal to VP naught sine 60. No, sorry. C is equal to YP naught. B is equal to that. And A is equal to minus 1/2 G. That's how I would set it up. So, and I think we got to be, yeah, right. Yeah, we got to be careful about the sign. So in this case, that's a positive 8.75, the way I have it set up here. So that's going to be equal to 8.75 meters. This guy is, we have to be careful about that velocity. You have to put in the right sign for it. And it's positive because the theta is up. So VP, well, I showed it here, is pointing in the positive direction. If you had shot the thing down, then VP sine theta would be negative. So you have to take that into consideration when doing this. So it's positive. I mean, we worked it out here, so we made it positive. But we'd already taken that into consideration. I didn't explicitly say something about it. And then minus GT, so that's going to be 9.81 divided by 2, 4 point, whatever that is. What is that? Is that 4.905?
Yes.
Yeah, minus 4.205. All right. Say again. Oh, and what's this guy? BP. So that's, be careful, you got to convert it too, because that's, no, that's 15 meters per second times sine of 60. Is that 0.5 or 0.88? Sine of 60 is
8.8660.
Okay. So that, so times 15. So what is that? Actually, you know what? Let me look at my calculator. I don't want to do it because you got to keep the significant digits in your calculator. You don't want to round it off. So you want to store those values as you work in registers as you work through. You don't want to use truncated values to make calculations. You only round it off at the very end. So that's something you want to start to practice now. No truncation till the end. do all that in 9 minutes.
Let's make professional football what it is today. There's not much you can say about someone who become a legend in his own lifetime, but I want to try. Mr. Hollis, one of the most rare individuals who is not content with things as they are. Sees things as they could be, works to make things better. As a rookie, he scored NFL record 22 touchdowns, capped off in December when he muddy field with 6 touchdowns. As great as he was on the field, his quiet wisdom and integrity made him a perfect choice. George Hallis. Hallis chose Yale to become the first African American ever in NFL history to rule with a white player in 1967, Brian Bigelow. They were completely opposite, found themselves to be that strength in football. A true story that captured American ideal of coming together that Brian saw. They became great friends, and it was Yale and Brian's bedside he tragically passed away before the season started. A sober part of life's journey. Reaching each point, however, is not as important as striving to get here. This is true in all professions, in all life's activities. There are doctors, lawyers, teachers, and farmers, all strive to do great business. We hear a lot today about how the American people have lost their dedication.
Okay. Again, these are just truncated values, but I'm keeping the whole thing in my calculator. So 12.99 meters per second, storing it in my appropriate register. So then my time is going to be equal to, I don't know which one it's going to be, whether it's plus or minus. I think we decided the minus would be, I shot it down negative, possibly. Well, because if that were the case, then the B would be negative. That makes, yeah, that's hard to see because it's, I don't know then. If B is negative, that's going to make that positive. So it's positive. That's not the one we want. So we would be adding it together. Negative, negative. So I think it's the positive solution that we want. I think it's the positive, so I'm going to go for that one first. So T plus is minus 12.99 plus square root of 12.99. So we do the radical inside. Square root. And then 4. Okay. A is C is plus. So I get all that to be 17.77 divided by 2 times A, which is minus 4. So I guess it's not that one. You're going to get a negative time. My bad. Um, yeah. So T plus gives me a negative 0.6. So you have 3 significant digits. Doesn't matter. That's not the right answer. It's not the right solution. Let's go to 3 significant. So 9 seconds. All right. So that's not the one we want. So let's go with T minus. In T minus, I have minus 12.99 minus 17.77 divided by whatever that is. 8.41 negative. All right. We call 1. We call 2. One. We call 2. 4. So this time I get something that seems reasonable. Is equal to 3.66 seconds. So I think the answer is 3.66 seconds. Anyone else get that? That's a good question about the speed of the boat being negative. Well, yeah, I guess you could, but the displacement is also negative. So I think that's going to work out. Technically, the displacement is negative because it's going in the opposite direction. So the two negative signs will cancel. In other words, if you look here, that's a good point you make. The final position is right? X. Final position. Yeah, I messed this up. The initial position is not 0. Well, neither one of them is 0. What did I say? Oh, that's for the projectile. I got the wrong thing. So that is XP. Yeah. So if you look here, this displacement is negative because you have X minus D, but D is a larger number, right? So initially it's, the way this equation really is before you put in our specific symbols, its final position equals initial position plus Vs times T. So if you take this over, the displacement is I guess what I'm trying to say is, like, if I solve this for you're trying to find D, right? So if you solve this equation, basically D is equal to a minus X plus Vs times T. So, and actually it's going to be minus 1 if you cross them up. Yeah, so if you put in if this is negative, which technically it is, then you'll have, yes.
Sorry, for the for A in the formula you use, it's minus 4.90 at the right.
4.9.
Yeah.
Okay. That's what I said initially, or no? Oh, my bad. So that's going to change the dates. Thank you, John. Changes. So I still don't give that a negative time that goes up, but this is going to be different now. So actually, what I'm saying, it just goes back to 9.81, doesn't it? It's just 9.81 again. It should be 9.81. Okay. So it also changes the top number too, though, because that was A times C. So this thing now becomes, so B squared is square it for A is 4. C is 8.7. And plus, so it looks like it's so it looks like that radical actually is 18.45. 18.45. So 18.5. It's like that. So it changes it slightly to 3.2. 3.2 seconds. Rounds to 3.20499. I guess that technically, let's just go ahead and take that to 3.21 seconds. Do that. So the minus signs will cancel out. That's the bottom line. You can't make it a negative velocity, but it's also moving in the negative direction. So when you put that into the equation, the negative signs cancel and you just get positive. So you just use the positive value. I mean, you know, whatever you want to do, it just works out that way. But what I did, you don't have to worry about that because it's implicitly negative, but it works out. It'll work. Actually, oh, I see what you mean. Because I put that in. That's a very good point. Does that change the answer? If I make that negative, no, because I didn't use that over here. So you're right. Yeah, I didn't use that over there. I didn't use that. For that time, we got independent of that. But here, yeah, you could do that. You could do that. That's right. Because maybe I should write the equation like that because it means that you're right. You're absolutely right. The way I wrote this equation, that should be negative. Right. Because this distance is smaller than that distance, so you need to subtract something from it to get, you're right. Yeah, absolutely. So it's probably the way I've been doing it is just putting it explicitly in the formula as opposed to putting it in the number that I place in there. Cool. So did people, so Dami, did you get that 3.21 for the time? So are there any other questions? So I don't know, Dami, did you?
No, I'm good.
Did you get 3.21?
Yeah.
I mean, yeah, I see, Roy. 3.20, I flushed it a little bit. I don't know. It's 3.20499. So technically, I guess you're right. It rounds to 3.20. So you do that. I'm sorry, Dami. What'd you say?
Oh, I said, yeah, I got the same thing.
Yeah. Oh, so then we put it back in. What were we trying to find? We were trying to find the distance. So when I put that back in, yeah, that should work out. Yeah, you're right. So now when I solve for D, D is going to be, yeah, because it would have subtracted it and D would have been less than X, so it would have been a problem. So when I take it and I put it back, oh, so I guess it's every place. So we had that negative here. So what does that do? Flip the signs around? When I equate them, this would be negative. And when I take it over, we're now adding the, you're right. So that's going to be a plus there. Yeah, otherwise that means that D would have been less than X, I think. It should be greater than X. So when we put that back in, let's see what we get. We get, so I can do that over here. And again, don't use the 3.20, don't truncate it, use the whole thing. So store. So we will have D is equal to 15 times the cosine of 60 plus, and if we convert that to meters per second, it's at 0.45 meters per second times 3.20 seconds. So D equals 3 sig dig, I get 25.5 meters. Yes, wonderful. Good. Yeah. All right. How do you feel about that? So took us to a break. Got 25.479 D here. Did you don't write it? For some reason I'm getting. Yeah, so it's a little bit off. I think, did you use round off? Like you can't use, don't use 3.20. You got to use the whole thing. Everywhere you have to use the whole thing, all the numbers. Don't round off to the very end of the solution. So when you report that solution, yeah, you use 3.20. But then when you use the number in a subsequent calculation, you can't use the rounded off version. You have to go back to the original. And so here, I'm not actually putting in 3.2. I'm putting in whatever it was, 3.2 and all the other stuff, because I saved it. That's called propagation error, which you want to avoid. So, Mike, it feels like it's that kind of thing. Yeah. Is that what you did? Yeah. Yeah, that's called propagation error, round off error, and we don't want that. Yeah. So I'm kind of getting mixed up. I had this conversation, but was it this class? It wasn't this class, was it? Was that this morning? We were having a conversation about round-off era and why, like, the classic. I mean, yeah, I guess it was early this morning, so we'll have it right now too. It was a slightly different kind. It wasn't round-off era per se, but it was kind of the same mathematical specificity that caused, or lack thereof, that caused the first space shuttle catastrophe. Does anyone know why? Was it, I'm getting mixed up, was it Columbia or Atlantis? Whatever the first one. That was before you were born, probably, but I was a junior in college, so that was, wow, so 30 years ago. Probably 35, 36. So, yeah. Does anyone know why the first space shuttle blew up? What the mistake was? No one? Donnie, do you know?
No.
It was the fact that, so there was an O-ring. An O-ring was, it's like at a seal, and it was a place where the gas was, the liquid fuel was going into this combustion engine where it would fire up. And you have to calibrate it to have a certain amount of gas go through the constant flow, I guess. And when they calibrated it, they did it in English units. The engineer did it in English units as opposed to calibrating it in SI units, meters, kilograms, seconds. So I think probably there was more flow going in than should have been. So, you know, these things are important. And it's, you want to start practicing it now to get, because once you do it, you practice it, you kind of get accustomed to being able to do it more fluently and efficiently, and knowing your instrument well enough to be able to store it in the registers and that sort of thing. So go ahead and do that. And, you know, in other places like medicine or something, you know, if you're calibrating the amount of medication someone needs for whatever, I mean, you know, if they need 3.2 milligrams, you don't want to give them 3.4 milligrams, 3.7 milligrams. You know, that can make a difference, particularly over time, or if you're monitoring like a heart monitor or something like that. You know, it's, so just, you know, get accustomed to paying attention to that detail, and then it will become somewhat second nature and not feel so awkward as it may at this point. So let's do that. Uniform circular motion is a class of motion that is a special case of rotational motion, a more general rotational motion. So right now we've looked at three kinds of motion: general in X, general in Y, with four kinds: general in X, general in Y, free fall, and parabolic. Centripetal acceleration is, or as I said, it's something that we kind of separate out and introduce at this point before we get to rotational motion much later in the semester. So we can identify this as perhaps a fifth kind of motion. Uniform circular motion, you know, it's fall, so if there were not coronavirus going on, we'd probably be going to the fair. And at the fair, you have things like a Ferris wheel that goes around at a constant speed in a circular motion. So uniform circular motion, we can talk about certain properties associated with that kind of motion. A Ferris wheel being an example. And this is what we call it, uniform circular motion. So characteristic of speed is, so even though you have something moving around, so let's say if I take something and twirl it around, like I could twirl around. So this ruler on the end of yeah, something like this, right? So the edge of the ruler is moving around in a circle. And again, to distinguish between velocity and speed, if you have something moving in a circle, let's say in the clockwise direction, as I was just illustrating at a radius r, the object at every point on the path, the speed of the object or the velocity of the object is tangent to the path. We saw that when we looked at motion in a curved line, curved path. So that's the velocity. So the velocity is changing because the direction is changing. However, the magnitude of the velocity is not changing, so the speed is constant. So speed constant, velocity changing. Since the speed is constant, since the velocity is changing, we have to have some kind of acceleration. Although the linear acceleration, A tangential, is 0. It's the rate, so A tangential would be the change of the speed along the direction of the velocity. So A tangential is the acceleration parallel to velocity. That's 0. A tangential, either parallel or anti-parallel to velocity. But a radial is essentially what we call the centripetal acceleration. And because the direction of the velocity is changing, that means that the centripetal acceleration is non-zero. If it's moving in a curved path, it's going to always have a centripetal acceleration. Now, we'll define that momentarily, but right now, let's focus on the speed, and we can develop some equations associated with speed. So considering speed, the speed is, it's delta x over delta t. But whenever we're moving in a circle, if we consider one rotation, the distance covered in one rotation we call the circumference. And we can define a time period for one cycle, which we call the period. So that we could write the speed of an object experiencing uniform circular motion in terms of the circumference and the period, which I'm going to use with a capital T. Period is the time per cycle. Frequency is the number of cycles per unit time. So the inverse, number of cycles per second, since in MKS we measure time in seconds. So the period is equal to the inverse of the frequency. Actually, before I say that, we measure time in seconds, units. We measure hertz in 1/seconds, which is, we measure frequency in 1/seconds, and that's called a hertz, and abbreviated HC. One of the most famous things that frequency is used for is the processing. We call it processing speed, but it's actually the frequency, the number of times that the processor spins. So gigahertz, whatever, it means that it's spinning that many times per second, which is pretty amazing. Processing speed, processing frequency, I guess we say speed, but that's not really, as I said, it's kind of, using the idea, talking about the concept in lay terms, but it's really processing frequency. You could say it's the speed at which it turns around, but that's not measured in, that's meters per second. Hertz is frequency. So I'll put speed in parentheses. This really should be frequency. So as I was saying here, the relationship between period and frequency is that period is equal to 1 over the frequency. It's not really a definition, it's just a relationship, really. And we could continue on and write, write this velocity in terms of circumference. That circumference is equal to 2 pi times the radius divided by the period. So that gives us a bit of a different relationship for speed based on the definition of speed, which is just displacement by time. But again, for one rotating object that's using, it's rotating uniform circular motion, that distance around is the circumference, and the time that it takes to do that is the period. Incidentally, the uniform in the title uniform circular motion refers to speed, not velocity. Obviously, the thing that is constant. Uniform is another word for constant. So uniform means it's obviously referring to the magnitude of the velocity. Yeah. Now I'm just going to move it forward. I could give a derivation of centripetal acceleration, but honestly, it's a geometrical derivation. It's kind of long, and you probably already know the formula that you was given in high school. So I'm just going to go ahead and write it down. Incidentally, does anyone remember the formula for centripetal acceleration from high school? Radio acceleration, anyone? Roy, where are you? Are you still around? Yes, Conrad, Roy Conrad. Do you remember, did you have physics in high school or physical science of any kind? Remember. What about you, David? David Edwards, are you there?
Yeah, I'm here, but no, I didn't have it in high school.
Okay. All right.
My first one.
Gotcha. Okay, thank you. Anyone? Abdul?
Changing the velocity for time.
One more time, I couldn't quite hear you.
Changing the velocity over time.
Well, that's the definition of acceleration in general. That's good, yeah. But this is that's the general definition of acceleration. But centripetal acceleration is a specific kind, and yes, Roy, does have something to do with the radius. You're right, Didier. There you go. So if everyone looks at Didier's post in the chat, yeah, it's the square of the speed divided by the radius. Roy, you were kind of warming up there. V squared over R is the famous equation associated with centripetal acceleration. And again, I could prove that, but it's a geometrical geometry and a little bit of calculus, and it's kind of a long using similar triangles and things. That's how it's done. But I'm going to move on because I'm not sure it's worth doing it in class time. But you might find some. You might find an explanation in text or online if you Google it. So that, and also what comes out of that derivation is that the direction of the acceleration, because it's a vector, so this is the magnitude, and the direction of the acceleration is such that it always points toward the center of the circle. And that's consistent. We did that earlier. We saw that the radial acceleration, remember when we did the stuff with, when we were on a curve I'll do it here. We had a velocity moving along a curve back when I said, okay, like we did stuff like velocity increasing along a curve. If the velocity was increasing, then, so we have V here. So it's moving in that direction, so V. But then we had a acceleration parallel to V, a parallel, I called it. And then we had one that always pointed toward the center of the circle, which I called a perpendicular. Okay, so that a perpendicular, then we called it a radial, but that's the centripetal acceleration. It's the same thing. So we already know that if that acceleration points toward the concave portion of a curve, in fact, one of the we did 3 examples. Remember, we had velocity increasing, velocity constant, and velocity decreasing. And I told you that if the velocity was constant, that meant that it would have to move in a circle. So we could use that same scenario here, that we've got the centripetal acceleration. At every point, it always points toward the center of the curved path. And the a parallel is 0. Why? Because there's no linear acceleration, because the speed is not changing, because it's uniform. So a perpendicular, always pointing toward the center of the circle, always perpendicular to the velocity at the point where the object is on that circular path. So those are the 2 basic properties. The magnitude of centripetal acceleration is v squared over r, and the direction of the centripetal acceleration is always pointing toward the center of the circle. AC points toward the center of the curve path. Okay, I've got to take a quick break and put some ink in these things. Sorry about that. Let me just, I didn't realize I was running out. So let that digest real quick. It only takes me a second or 2 to fill these things. I'll be right back. All right, back. Hopefully this works. Yes. Yes, wonderful. So, AC points toward the center of the path. Yes. We could take the what could we do? We could, oh yes, I could write the centripetal acceleration in terms of period and frequency by combining, let's number these equations. So equation one, I guess this definition, so just leave that. Equation 2, 3. So if I substitute 1 into 3, I can get a centripetal. So this is centripetal acceleration in terms of speed, but I can get it in terms of frequency and period. So something like AC equals v squared, but v is 2 pi r over the period. So putting that in, it's going to 2 pi r over the period, quantity squared, but then I have to still divide by the radius. So 1 over r. So when you do that, you get squaring it. So AC is 4 pi squared r squared over the period squared times 1 over r. So one of the radii, radius cancels, left there and leaving 1 here. So you can say that the centripetal acceleration is equal to 4 pi squared r divided by the period. Or you could write period in terms of frequency and substitute equation 2 into equation 4, 5, 6. So substituting equation 2 into 6, we just write along here that it's a centripetal acceleration is also equal to 4 pi squared r times the frequency. So these equations here are also valid. So this guy is equation 4, centripetal acceleration as well. So that's it. That's quick. That's a quick introduction to centripetal acceleration, focusing specifically on motion. So we'll come back. There's more that we can say about this because we can relate that to Newton's second law. But I wanted to introduce that now so that we actually have that once we get to that in forces. And maybe it's worthwhile doing a problem or two just to kind of hone that in, specifically from the point of view of motion. And maybe a Ferris wheel problem is a great one. So we could do something like, let me make a problem real quick. Let me think of something that might be nice in relating to what we've done before. So yeah, so you're going to see problems like this. Let's say that you have a
windmill.
wonderful. Let's go with a windmill. Let's say you've got a windmill and the windmill is turning. It makes 1 revolution every. So yeah, so we need the radius. So let's say it's a big windmill, and I don't know, like maybe the wings are half the size of this building. So 1 floor is at 1, 2. Let's say a floor is 3 meters, so 6 meters. So we've got the I don't know if they call them wings or wings of a windmill are 6 meters long. Draw out a windmill. So yeah, maybe we got a windmill that looks something like this. Very crude windmill. So here we've got a little circular thing there. The wings come out like this. So we got 3 wings. whatever. So it's spinning around, right? And so we can say that the radius, r, is 6 meters. So given r is 6.0 meters, we say that the windmill turns one rotation every just guessing, 25 seconds. So makes one revolution every t equals 25, every 25 seconds. So what do we want to know? Let's label these flaps. One, two, three. Let's say that I don't know, this is coming off the cuff. I'm making this up really. So let's say that it's kind of a crickety Ferris wheel. And there was a loose piece of panel or chipped wood right here at the edge. And for some reason, maybe, you know, a gust of wind came and knocked it off or something. And right when panel 2 was at the very top, at the vertical. And so this thing comes off with a horizontal speed that is the speed of the windmill. So it comes off, it's like horizontal. So basically it turns it, when that happens, it's kind of like the problems we did when we shoot an object off with a horizontal speed. If you assume that there's no drag or anything, then this thing is going to fall with parabolic motion, right? So the thing is spinning around, comes loose right at that top. And so then as the thing continues to spin, this thing basically shoots off and falls down. So what I want to know is, so you can see it very easily combines it with parabolic motion. So I want to know basically what is the range? How far did it travel here? And I guess I should give you that we also need a height here. So let's say that the radius of the flaps is 6 meters, but let's say that the thing is pinned here, like this height above the ground, got to give that something, I don't know, make it 8 meters. So 8.0 meters above the ground. So you need that as well. So I think that's enough information, actually. That's all windmill is. So that's 6 meters, but that right there is 8 meters, right? You know that it makes one revolution every 25 seconds. And I think that is all you need to know to do the problem. It might not look like you have enough information, but you do. That's a pretty good problem. Go for it. So yeah, so let me write conclude. So the windmill is attached 8 meters above the ground, or the wings, 0.0 meters above ground. If a piece of wood we can give it a mass, M equals 20 grams. Flies off wheel 2, flat 2. Find delta X. So if a piece of wood, 20 grams, flies off of flap number 2, at the top of the flap, when the flap is vertical, in this position, find delta X, the distance that it moves in the horizontal before it hits the ground. Oh, work on that. So I'm gonna get some tea here while you're starting that, and then we'll come back and finish that up. How much time do I have? An hour, 50 minutes. That's enough time to finish this up and get started to introduce the first law of motion. It starts with discussion of inertia. Mass. So see this. Okay, let me try to move this along a little bit. Where we go. Well, we've done problems like this before, right? Where I gave you this, basically, you don't have the initial velocity, so you have to figure it out. And you can figure it out using this, this information that I've given you here. If you technically don't have to use, I could have asked some other things, but we'll just about. But you know, given that you now have this, you can figure out what this what the velocity is as it shoots off, and essentially, you have the period. The period is 25 seconds. So, period is 25 seconds. So I can, and you also have the circumference. You can use because you can figure out what that, basically what the velocity it has is as it moves around, and that velocity, that speed, what the speed is, and that speed becomes the velocity that is projected off with at the top. That's the magnitude. So basically, that speed or velocity is 2 pi times 6 divided by 25 seconds. And so that will give you the speed. And that value is, get the number, um, 1.5 meters per second. Remember to store it. So really it rounds to 1.51 meters per second. So now I have the initial velocity. That becomes, for my projectile motion problem, that becomes the initial velocity in the y direction. The initial velocity in the x direction, sorry, this initial velocity in the x direction, the initial velocity in the y direction is 0. The acceleration in the y direction is now, and again, don't mix it up. While it's on, while the piece of wood is on that thing, it has a centripetal acceleration, and that's all. But as soon as it flies off, now that centripetal acceleration is no longer, and it has, you know, basically just acceleration in the y direction, which is g going down. So ay equals negative g. And so you could do, you know, the same time it takes. So basically, you have the 5 basic equations. We were just using those. One is, or 7 basic, but one is the x translation, the delta x equals that velocity, vx naught, times the time. That comes from the equation of motion in the x direction, horizontal equation. The 2 unknowns that I don't have are x and t, just kind of like in the last problem. So now I have to find t. And where do I go to t to get the, well, it's the same time it takes to fall down. So I usually call that equation 3 or 2, I think. So the other, just listing them in the order that I've always listed them, you have v dy equals vy naught minus gt. Not that one, but this guy, vy or delta y equals vy naught times t minus 1/2 g t squared. And vy naught is 0 because it's completely horizontal. So I can get time from this guy. That time is equal to 2 delta y divided by g and the square root of that. So equation 4 gives me t. I can take t and put it back into 1, and that will give me my displacement. One thing I want to say about y is that the y is going to be the distance from the ground to where the thing is pinned plus the distance of that one fan, which is 6 meters. So the total distance, I guess, is 14 meters. So the delta y is 14. Let's go ahead, and I'm curious to see how much it will travel. I don't know, I just made it up. So T is equal to, oh, the material there. T is equal to 2. We'll go ahead and put in the numbers, and then we'll come back. See. Okay. 2 times 14. Using 6 and 1, given that velocity over there. Again, no truncation. In the end, you have delta x equals 2.55 meters. Let's get an idea of what's the value of centripetal acceleration, how it relates to g, because that gives us something to compare intuitively, right? G 9.81, right? I think the human body can't really survive more than like 7 or 8 Gs. That's 7 or 8 times the acceleration due to gravity at the surface of the Earth. So what would something like on a Ferris, this is probably a reasonable number for like how fast you might be going around on a Ferris wheel. So let's calculate what the centripetal acceleration is and compare that value to 9.81 to just get an understanding of the kinds of accelerations, centripetal accelerations that you might feel on an average, on an everyday basis or in real life. So the speed we calculated was 1.15 over there. So yeah, so the centrifugal acceleration, AC, would be equal to that 1 point, or that, I flipped this around, had a dyslexic moment. I didn't change it from my calculator, so it's still in there, 1.51. And so 1.51 meters per second quantity squared divided by 6 meters. So AC is equal to, I stored that, so I gotta recalculate it. 6 times divided by square. So square that and then divide by 6. Wow, so it shows you it's very small acceleration, 0.3379 meters per second squared. And I think that's actually a reasonable number. So that's, not even 1 meter per second squared would you experience, not even a half with a certain situation like that.
Professor,
Yes.
sorry, how is Vy not 0?
Because when this object comes off of the wheel, when the wheel is completely vertical, that velocity it has is horizontal. Remember, I drew that picture where I said the velocity is parallel to the curve at every point along the curve, right?
Mm-hmm.
That's the nature of the tangential velocity. So with this Ferris wheel, like this is the curve that is traveling on. It's going around like that. But at that very top, the velocity that it has is tangent to the path. So if it comes disconnected to the wing at that point, it's going to move off with a horizontal velocity. So it doesn't have a velocity in the vertical direction. It basically is the same as me flicking a penny off a ledge, like I've done for you. We've done several examples of that.
Yeah.
So the initial velocity of free fall is 0. So that's why.
Okay. Okay.
Does that make sense?
Yeah.
Yeah.
All right, thank you.
Good. Anything else? That's a good question. Anything else? So yeah, that's it. All right, let's move on. Yeah, I did mean, sorry about that. 1.5. Oh yeah, I didn't see you ask me about that earlier. Yeah, we did. 2.55 meters. So I took that time, plugged it in here, using that velocity, and this is the answer. So 2.5 meters from the, sorry, no worries. Cool, cool. Anything else? Sorry, I didn't sleep so well last night, and it's 7 o'clock in school, teaching all day. But I love it. equation 4? Where did the negative sign go? Equation 4. They canceled out, right? Because the delta y is inherently negative. That's a good question. Good question, right? But we've talked about this before. That's why I didn't mention it. Because it's going down, right? It's final minus initial. So the final is 0, and the initial is 8. So it would be 0 minus 8. So you'd have like a minus 8, and then that minus sign over there, so they cancel out. How do you get AC? It's from the definition. It's v squared over r. So it's the definition that we used. Centripetal acceleration is v squared over the radius. So v squared, we just calculated somewhere. Oh no, we did it over here. And the radius is 6 meters. Yep. Yeah. How did you get AC 700? This. Oh yeah, that's what you're asking. Did I make a mistake? Might have made a mistake. It's just that squared. So what you gotta use, don't use the truncated value. So we call that square it and divide by 6. Yeah. Anything else? I missed the question. Someone asked me about the 1.15. Oh yeah. That's good. That's twisted it around. Anything else? So let's move on a little bit. We're done before we leave. Isaac Newton. Isaac is king. Isaac is, in my opinion, the greatest physicist that has ever lived. Even more so than Einstein and all the people you've heard of, Hawking. And, you might think I'm saying, Einstein usually is credited with. That's only because he's been the most recent. After a couple hundred years, you kind of forget. But Isaac Newton was amazing. I mean, I honestly, Einstein is, it's pretty out there as well. But Einstein, like one thing you could say quantitatively is even Einstein would say that he didn't feel so confident in his mathematical abilities. In fact, the rumor is that he would consult with some of his mathematical colleagues before he would publish papers because he was a bit insecure about it. Now, compared to me and you, Einstein probably didn't have any, relatively speaking, it's all relative, right? Probably would run circles around us, but compared to someone like the best mathematicians of the day, it wasn't, he probably, some of those individuals could probably challenge him. People like Heisenberg, Dirac, Schrodinger, people like that were more analytical. But they didn't have the insight that he had to be able to look at a problem and look at it from a completely different perspective. And he did it consistently. Einstein's model of matter was the model of a solid was the first paper he published. Then he had the photoelectric effect, which basically ushered in essentially the modern age and began the trek for modern physics, which ultimately culminated in 25 years later or 20 years later, the development of quantum mechanics, which is credited around 1925. So Einstein was one of the first individuals. So let me give you a bit of a history lesson. It's important to put all this in context. Isaac Newton. So Isaac Newton, every century, I don't know if I talked, it was in this class, maybe I did. I'll just give it a quick rundown. Every century there's, the geniuses, like Copernicus, Kepler, and Galileo. Those guys were like 1400s and 1400s, 1300s into the 1500s, 1600s. And, they basically focused on astronomy. The big strides at that time was understanding that going from, an Earth-centered universe to a sun-centered solar system and beyond, ultimately realizing that our solar system was part of, even a bigger construction in galaxies. So it started with that, with those guys. And then essentially, then Isaac Newton comes along and just completely jumps levels of insight from Galileo to basically the modern age. Essentially, prior to Kepler, Copernicus, and Galileo, there wasn't much progress literally for 2,000 years. Basically, the Roman Empire fell. Egypt, in the library at Alexandria, was burned in like 200 BC. And the Roman Empire actually fell around 500 or so AD. But even basically essentially from about 300, there was progress that was made up to about 300 BC. The Romans invaded Egypt, bunch of civil wars, and basically society kind of began to fall. And it took a couple hundred years for the society to fall, but basically progress essentially was stunted, around the time of Jesus' birth. And as I said, it took about 300 years for things to really just cave out. But it did finally happen when the Roman Empire fell. And from around 500 AD, literally until the 1400s, basically nothing was going on in terms of our evolution scientifically. It's really incredible. It was just nothing. And so you got these guys come in, Kepler, Copernicus, Galileo. People were still thinking light was something that traveled on ether. Ether was literally a concept that was presented by Plato and Aristotle. So that's the progress that we made in a millennia, over 1,000 years. Well, actually, it was more like 1,500 years. Can you believe that? That's really, 1,600 years. And you compare that to the progress that we've made in the past 300 years, it's just mind-blowing. But the person who really jump-started it was Isaac Newton. I mean, really kind of kicked it in high gear. He didn't jump-start it because I guess Galileo and those guys, the astronomers jump-started it in the Renaissance. But Newton just put it in overdrive. And even now, I don't think there's anyone, not even physicists, there's no single scientist on the face of the earth in the past 2,000 years that has contributed, in my opinion, made a contribution intellectually that has had more, not even remotely closely related. It's hard to put it in context unless you can understand the relative value of these developments. And it is a little bit difficult, I think, unless you study these things. But I think Isaac Newton is literally head and shoulders above Einstein. And Einstein, you know what Einstein did. And the reason is that Isaac Newton gave us basically three things. Any one of those things could be considered, certainly, they weren't giving Nobel Prizes at the time, but even in the context of Nobel Prizes, the impact that they have on our society, of Nobel Prizes, any one of these three, you could probably rank the hierarchy of Nobel Prizes, right? And any one of these three would certainly be at the top of any list that anyone would come up with. But he did it three times. So Isaac Newton, who lived between us, 1642, I think, 1727. Gave us three basic things. Now, he does have three laws of motion, but outside of the three laws of motion, that's just one. The laws of motion is one contribution. So he gave us gravity, the universal law of gravity. He gave us the laws of motion, which are actually separate. They're related to, there's a relationship between the laws of motion and gravity, but they're separate. Basically, the laws of motion. Now, we didn't come at it from that point of view. I came at it from a basic mathematical point of view. But essentially, all those equations of motion that we've been working, they are derived from Newton's force law. And we looked at very simple laws of motion, but you can basically take Newton's force law in any kind of force, derive any kind of law of motion. And there are different laws of motion depending on the forces that you're in. The forces that we are in for these equations are essentially gravity, which we look at it from, weight, from the point of view of Newton's law. It's not the universal law. And just any kind of arbitrary acceleration. So laws of motion. And the final thing, which is, again, each one of these things almost like tops the other. But I don't know how many people know this. I'd like to see a show of hands. Well, actually, what is the third law? The third thing that Isaac Newton contributed. Does anyone know? If you don't know, it's going to probably blow you away. Anyone? Probably had no idea or had no idea.
Is that for like every?
I do. What? Tell me.
Is that for every action there's an equal and opposite reaction?
So that's one of the three laws. The laws of motion. Well, we can list them out. Again, this is not what I'm talking about. The three laws are the following. The three laws of motion are the first law. For every action, an object will stay in motion or at rest unless acted upon by a net external force. So that's the first law. And the equation associated with that I'll teach you is net force equals 0. The second law is, you can say it several ways, but F equals ma, net force on an object equals mass times acceleration. Another way to say it is that the net force on an object, net external force, is equal to the time rate of change in momentum. That's actually how Isaac Newton initially said it. But the second law is the net force equals mass times acceleration. And the third law, which is what you just mentioned, Abdul, is that for every action there's an equal and opposite reaction. So the third law is the law of action and reaction. So those are the three laws which are themselves comprise the laws of motion. That's one unit contribution. So that's not, these three contributions are separate from the individual three laws of motion. Okay. So the third contribution is something else. So the universal law, and that's gravity, right? That's basically discovered gravity, apple on the tree. And universal law of gravity has an equation associated with it. It's that the gravitational force law is equal to G times basically between two objects, but you can describe it with more, but mass 1, mass 2 divided by the distance between the two squared. So that's the universal law and the mathematical equation associated with it. This is the laws of motion and the basic kind of mathematical equations associated with that. This guy, the mathematical equation, is just F12 equals negative F21, right? Action, reaction. If you force on something, that thing forces back on you with an equal and opposite force. But no, I'm asking, what is the third major contribution that Isaac Newton gave to the world outside of these other two? Anyone? All of you have studied it. If you've gotten this far and are taking physics 1, then you've studied this thing. No, not conservation of energy. No, people suspect that Isaac Newton knew about conservation of energy, but he didn't publish it or say anything about it in his force law, his Principia. Oh, by the way, that's where he published all these things, except for the third one. He didn't say anything about the third contribution. That came later, that people realized that he had discovered it, and he didn't say anything about it until someone else discovered it. And he said, oh, wait a minute, I did that also a couple years ago. And no one believed him. And then he published proof, and then everyone realized that he did. So that's actually a hint, because technically now there are two people who are credited with contributing this thing. The person who initially presented it to the world, and then people then had to give Isaac Newton credit because they realized he had actually done it and didn't tell anyone about it because he was more focused on physics. It's actually not a physics, it's not a physics concept directly. It's really interesting. It's going to be surprising. No one knows? Let's see here. Oh, the Principia. So all these things were published in his book, the Principia, and that was published around 1686. And while you're still thinking about this, there's a story about this. In fact, so you know there's a new Cosmos out now, Cosmos 2020 with Neil deGrasse Tyson. I think it's Cosmos Undiscovered Worlds or something like that. So it's probably a good thing to check that out. They've got 2 shows so far. I think it started a few weeks ago. But several years ago, there was a remake of the Cosmos from the 70s. And so it was Cosmos. It was also Neil deGrasse Tyson. I forget what the subname, Cosmos something. But anyway, Cosmos, what is it? Let's see. Well, Space Odyssey, yeah. Right? Yeah, I think it was Cosmos, a Space-Time Odyssey. And they had about 13 episodes. The third episode, I believe it was an episode that discussed Isaac Newton and how he came up with the universal law of gravity. And it's worth, if you can get a hold of that, taking a look at. And all those are really interesting. Look at that old season and even the new season. I haven't looked at any of the shows of the new season, but it's probably pretty good. But yeah, so basically, Halley, as in Halley's Comet, and Hooke, Robert Hooke, i.e. Hooke's Law, back in the 1600s, they were trying to figure out, what force caused comets to move around the sky. And Halley kept saying that he knew it, but he didn't because he was kind of an arrogant guy who wanted to be the smart person in the room all the time. And so they kept asking him to prove it, and he said, well, I'll do it later. I can't, and just whatever. So finally, Halley got frustrated, and he went over. You remember there was this young genius working at Cambridge, which was Isaac Newton in his early 20s. And he went over to talk to the guy and went into a very messy office and everything. The guy was kind of an absent-minded professor type, Isaac Newton, apparently. And so he asked Isaac Newton, we've been working on this problem. Do you want to come join us for coffee and kind of talk about, we've been thinking about this, trying to figure out what causes comets to, what is the universal force that dictates them. And Isaac Newton said, oh, I figured that out a while back. I know already. I know what it is. He said, really? So he says, well, prove it. And so in this messy office, Isaac Newton starts fumbling around looking for papers, trying to find where he proved it. And of course, because Halley was accustomed to that kind of behavior from Robert Hooke, who, by the way, Robert Hooke was the head of the Royal Physics Society. So these were the top physicists, not only in Britain, but in the world. This is their little club. Halley says, okay, whatever. Just mail it to me when you find it. So Halley leaves, and sure enough, about 2 or 3 weeks later, he gets this package in the mail. And basically, it's the fundamental notes of the Principia. And not only has Isaac Newton laid out the universal law of gravity, but he's laid out his 3 laws of motion as well. And the guy just didn't tell anybody. He published it, he did it, wrote it, and just stuck it in a corner somewhere. And it would never have been known if Haley hadn't gone. And then Haley looks at this and he can't believe what he's looking at. And he goes and he goes back to, he's like, dude, like what? Like, you got to publish this. And, you know, Isaac Newton had a lot of issues from childhood. He was kind of a recluse type personality. And, you know, no friend, he's never married, anything like that. He was just, you know, kind of a different kind of guy. And so finally, you know, as it turns out, thank goodness, Haley actually had a publishing company. And he and his wife get together and they put all their money into publishing this thing because Isaac Newton wasn't going to do it. So they write it up, they edit it, they republish it because it's just a bunch of notes, right? And they published the thing in 1686 through Haley's publishing company, and it becomes the Principia, which is like, you know, basically almost on the level of the 8th wonder of the world type thing, you know. So that's, and they talk about this, they dramatize that in this space-time odyssey. So it's worth going back and looking through. All of them are really good, and so I'm excited to see what the new season is, if it's as good as the, which I'm sure it will be. But anyway, so that brings us, we're almost done here. Does anyone remember or know or thought about or Googled what Isaac Newton's contribution is? Spectrum? Ah, someone got it. Sure. Yeah, dude. It's mathematics, Abdul. Yeah. Isaac Newton invented calculus. Let me just let that sink in. Like all calculus, all of it. Like calculus 1, 2, 3, differential equations, everything. The whole concept of limit, that stuff, that boring stuff that you study in the first couple of chapters, limits, and all of that. Isaac Newton was Isaac Newton's brainchild. And the reason that he did it is because he wanted to prove this. Let me tell you what these guys were doing. This is just how meticulous, and really kind of all of them, you got to give it to them in terms of expertise and excellence, and just how difficult it was to get us to where we are, where we do things with phone. You know, I'm talking to you now with a cell phone. I mean, like electromagnetic wave. Basically, that light that at that time when Isaac Newton was doing this, people thought was still on ether. That light ultimately is electromagnetic waves. So it just shows you just how far we've come, where even in Newton's time, people were still, in fact, even after he did this, it wasn't until 100 years later that James Clerk, the next century, actually this is, no, it was 200 years later. Basically, James Clerk Maxwell discovered light in around the time we were fighting the Civil War, 1860s. Up until that time, people still, even after all of this, still thought they were still looking for ether somewhere in the universe. Like this, there's supposed to be this stuff that was where light traveled on and was in the air. And he proposed the electromagnetic spectrum, speed of light, all that in 1860. But it took about 40 years for technology to catch up. And the first X-ray was taken, I think, around 1890-ish. And even in that 40-year period, because James Clerk Maxwell was really young, and he was young, kind of like Einstein, also very young at the time that he wrote his paper, people didn't believe him. They didn't believe him. Even some of the leading physicists didn't let go of the idea of looking for ether until I think, I forget who took the picture of the first X-ray, but which proved that electromagnetic waves actually did exist, and that you make devices like X-ray machines with them. So, you know, but the point I was going to make here is that and it started with Galileo and the Kepler guys. These Haley and Robert Hooke, they were still doing it the way that Galileo and those guys had done it 100 years before. The premier technology at the time was telescopes. So telescopes in, 1600s was like the iPhone now. And so they were literally looking at the moon and the and the planets that they could see, and meticulously documenting their movement across the sky with a telescope. And they would have generate this, hours of data, and then plot it so that they could plot what the curve looked like based on, distance from the center of the earth is kind of how they would try to. And so what they were literally plotting out the path, the equation of motion, but graphically the equation of motion. So you know how, like I was teaching you that when we were plotting x versus t, that gives a path, right? So, or x versus, well, they were doing y versus x, but whatever, that you could do it however you want, but that gives they were trying to figure out the functional form. So like with linear motion, constant motion, that functional form is a line. The functional form of free fall motion is parabolic. We've talked about that. They were looking at the planets and trying to figure out what the functional form was, but they didn't have calculus. So what they would literally do is look at it and record the data and plot it. You know how meticulous that is? And the problem is Isaac Newton started doing it the same way, but he realized that there's got to be a better. First of all, he figured out what it was. I guess he guessed that it was a 1/r² law, this thing. So he actually did what they couldn't do because he got the answer. But he had to have the insight to realize that it wasn't enough to just guess the answer and then see if the equation fit the form. He wanted this because he realized that it could, but what if it's not exact? What if the error is so small that you can't see it from a graphical point of view? So you'd have to have a theoretical way of figuring it out. And that's the thing that's so brilliant, is that concept didn't even exist, the idea of figuring out something theoretically, because you would have to have calculus. So I'm guessing that's why he invented calculus. Like, you had to have the concept. It's just incredible. It's like trying to build a house when there's no concept of a brick, but then conceiving that, well, maybe there is something that I could use better than straw. Like it's just incredible. And so he devised this concept of a limit. I think that's probably what was happening. The whole idea of the apple hitting on the head. He discovered gravity. Yeah, he kind of guessed at the physical form. But then once you guess, and yeah, you can kind of match it to your data and see that it works. But you only have certain data points. It's not continuous, right? Because you're just looking at it through a telescope. So it's not like the data is absolute. And he had to realize that. And so how could I figure out, theoretically that, basically find the, fit the curve exactly, right? So you would then have to create some kind of concept to be able to do that. And so what I think he did is realize that you have to start with this idea of taking time to the zeroth limit, right? Because what would happen is with the data points, there's always going to be some different, not differential, but some delta time between the path that the planet is moving, right? And with the naked eye, no matter how good you are, and they were very good, there's still always some delta t that's an appreciable amount of time, like a half a second, even if it's a quarter of a second, that's still a lot of time. And so you can't really do it theoretically. You can never do that because there's always going to be some delta t. But what I'm guessing is he thought, well, what if you go to the limit of, just keep cutting time in half? Then you could actually get a correct curve of what you would have it would be a continuous data point of the path of the planet. But that becomes a theoretical concept. And I'm guessing that from that point, he developed the idea of the limit, which ultimately came to something that he would invent called a derivative. And once you have that, and then understand the reverse of that as an integral, then you have the theoretical basis to be able to prove this thing is correct theoretically and actually fit the curve exactly. Can you imagine that? So this guy does this, invents calculus, and then when he publishes a paper, he doesn't tell anyone about the calculus. And I'm guessing that he didn't do that because who would know what it is? You know, but because he had done the calculus and theoretically proved that it was right, he had the confidence to know that all of this was right. And so then they published it. And 2 years later, sure enough, Leibniz, I guess, is the guy, I think it's a Swiss physicist or whatever, maybe, I don't know, German or whatever, Austrian, whatever it is. He invented calculus and presented it to the world. And then Isaac Newton said, oh, wait a minute, actually, I did that, sorry, a while back. And then they was like, yeah, right, you know, people. And so, but then, you know, he showed them and then, yeah. And so now both Leibniz and Isaac Newton are credited with inventing calculus. So that just shows you, I mean, like it's really hard for me to put anybody above Isaac Newton's contributions. I mean, think about this. You know, again, if the first two aren't impressive enough, you know, the guy invents calculus and he's such an humble person and so focused on other things that he doesn't even tell anyone. Like that's how little calculus meant to him than, you know, than what his real focus was to understand, you know, the physical principles that he introduced. So I'm going to leave it at that today. We'll start with that, and then we'll start with going through the first three laws. We'll get to gravity at the end of the course. But I just, you know, I like to spend about 15 minutes, 20 minutes just paying homage to Isaac Newton, because I think it's important for you to understand just how much it took for us to get to a place where we can study this, you know, what we're studying right now. I think it puts it in context, and it gives the relevance and just the sacrifices that people made in order to, you know, have the knowledge that we now to some degree take for granted. Again, you know, science, you know, like we know that there's global warming. We know how to handle a pandemic. All of this knowledge has come, people who've sacrificed and, you know, given expertise to be able to survive in the world in an efficient way in which we do. So whenever you kind of